Hello everyone, this is Mike Dowding with the SD Minds Physics Department, continuing with Chapter 7 material, Chapter 27 material. I realized after having an office hour session, I did not cover the concept of power with resistors. So I'm going to go ahead and do that first, and then we'll jump into one of the combination resistor circuits involving series and parallel resistors. So just as a review, back in Physics 1, power was defined as the amount of work done in a specific time, and work was the change in energy. And so what we want to do, we'll go ahead and start with really the only energy expression that we have from the last couple of chapters, which is potential energy. And in chapter 25, we got this equation that says that the potential energy can be represented as the charge times the electric potential, or as we're starting to call it now, the voltage. And so if we apply our definition of power to this potential energy expression, the first thing that we need to do, first of all, is we have to have a change in energy. So we'll go ahead and throw a delta in front of that potential energy term, so that tells us potential energy is changing. But first rule of algebra says what you do on one side, you have to do the other. So that means I'm going to also have a change in potential. And now we bring in the time component. So we'll change our potential energy with respect to time. That means we have to change this side with respect to time. And over here, we get change in energy with respect to time, which is power. And then you might be tempted to combine these two, but that's not what I'm going to do. Instead, I am going to combine the change in charge with respect to time. Because when we say that there has to be a delta on both sides of the expression, well, who's to say that that delta has to be with the potential? Maybe we could have a change in charge instead. And specifically, what we're after is something like in the case of a resistor, where we have a constant potential being provided by the battery. That battery is going to produce some current that goes through our resistor. And so it's that combination of change in charge over time that we can call current. And then the last piece there is the potential. And we now have the power for really any given element inside of our circuit. If we apply some values, so maybe our battery is 20 volts, and we'll do a 10 ohm resistor. So what is the power associated with that resistor? And again, remember the definition. Power is change in energy with respect to time. What we are doing is we are taking energy out of the battery. So our battery has stored some amount of potential energy, but then when all of that charge gets to the resistor, that's when the material of the resistor starts to resist the flow of current, and that causes quite a bit of friction which is going to generate some heat. And so in this chapter, more than once, we're going to see the phrase rate of energy dissipation. So the energy dissipation is the heat, and the rate is the time dependency. So we do in fact meet both criteria of change in energy with respect to time. And you're probably more likely to hear this phrase than you are to be asked what's the power of the resistor. It just seems to make more sense saying how much energy is your resistor wasting, basically. Well, we can find that out. The power, or rate of energy dissipation, for the resistor is going to be the current passing through the resistor times the potential of the resistor. Well, that means we need to know the current. Ohm's law, V equals IR, will tell us what the current is. We have potential of the battery, resistance, 20 over 10 makes 2. So we have 2 amps. That's the current. 2 amps. And a potential of 20 volts gives us 40. And now we need the units for power. Now we can go with the units of current times voltage, which would be amp volts, but if we remember from Physics 1, the actual unit for power is a watt. So we have 40 watts as the power associated with that resistor. So that resistor is basically throwing away 40 watts, or another combination of units that we can use are joules per second, because that is the definition that we get up here. Energy is in joules, time is in seconds, so joules per second. So our resistor is throwing away 40 joules of energy every second. Where is that resistor getting the energy from? Well, we already know that. We're getting it from the battery. If the resistor is dissipating 40 joules every second, then that means that the battery has to provide 40 joules per second to the resistor. And that is something that we can confirm by using the exact same expression, because this expression for power is not just for resistors. I can ask, what's the power associated with the battery? Well, 2 things I need to know. How much current is the battery providing? Well, I know that. It's 2 amps. And what's the potential associated with the battery? It's 20 volts. So, 40 joules. And this goes directly into our conservation of energy expression. If we're going to be throwing energy away through the production of heat, that energy has to come from somewhere, and it's coming from the battery. So P equals IV, that is one expression that we can use to describe the power. But what if we went back to Ohm's law and said, well, can we do some substitutions? What if we substituted V for IR. In that case, we would get I times IR, or P equals I squared times R. Now we need to confirm that this is in fact going to work, and we can do that by using the values that we had over here. I need to know the resistance value, which, let's see, there we go. We had a 10 ohm resistor, and we had 2 amps for the current. So 2 amps for the current times the value of the resistor. 2 squared is 4, times 10 is 40. So there's our 40 joules per second, or 40 watts. But there's another substitution we can make. What if instead of substituting V in the first equation, maybe we take Ohm's law and we rewrite it for I. And then we replace I in the top equation. So I equals V over R times V, which becomes V squared over R. And we can just as easily confirm this equation as well, because we had a battery of 20 volts, a 10 ohm resistor. 20 squared is 400, divided by 10 is 40. So all 3 of those equations can be used to find the same power value of our resistor. However, only this equation can really be applied to the battery, because each of these second equations specifically have the resistance value of the resistor. But that top equation, this can be used for batteries or resistors. Okay, so that's the power discussion that I wanted to have. And now that we know how to find the power associated with any resistor, we can actually extend the list of questions that we can ask about these circuits that we're going to be working with. So now on to the combination circuits. So we're going to do a combination of series and parallel resistors. So I'm going to draw in some resistors. I think this will probably be enough. I'll see if I can make, oh. I was trying to make this a bit cleaner and just erased everything. Okay. Battery. Resistor 1, resistor 2, resistor 3, resistor 4, resistor 5, we'll call this resistor 6. Okay. Now in a previous video we spent some time working on how to substitute all of the other resistors in the circuit with one resistor that we called the equivalent resistor. And if I can do that, then my work becomes a lot easier, because then I can use Ohm's law to relate the current coming out of the battery to that one equivalent resistor. And that would be very helpful to me to know how much current is coming out of the battery, because then I can start stepping through this larger circuit expression and start figuring out what are the values associated with each resistor. And with that, I'm going to put our resistor values over here. And I'm gonna make myself a table. I'm going to put the actual values of the resistors in the first column. In the second column, I want to know the current passing through each given resistor. And in the last column, I want to know what the potential difference is associated with each of those resistors. And that's going to be in volts. Trying to write small here. It's not working very well. All right, so first things first, I need values for these resistors, and I'm just going to make up values for these resistors, and I'm not feeling all that imaginative, so I'm just going to go down and say 10, 20, 30, 40, 50, 60. Now, I would, if you're writing this down in your own notes, I'd like you to leave some room below this table, because I'm going to add some stuff here as we go. Okay, so I have all the resistor values. I also need a value for the battery, and I'm going to assign a rather large value to the battery. I'll say 200 volts, just so we have, or so we don't get a lot of really small numbers along the way. All right, if we look back at our original circuit here, there's not really anything that I know about any of these resistors. I don't know how much current is running through them. I don't know what the individual potential values are, and so we're not really in a good place. However, if I could figure out what the equivalent resistance of the circuit is, since I already know what the value of the battery is, then I could find the current, and then I could use that current to start figuring out other things in the circuit. So that's what we're going to focus on right now. I want to take this large circuit picture and reduce it down to the equivalent resistor picture. But to do that, it's going to take us a couple of renditions of redrawing things. So if you don't mind, I'm going to erase the equivalent resistance circuit. We will come back to that, but we're going to take this a step at a time. We know how equivalent resistors are made if we're dealing with series or parallel resistors. And let's see, what would be a good place to put that? I'll put those over here. We'll say series resistors, parallel resistors. Series resistors have the same current, different voltage, and we find the equivalent resistance by taking a direct summation of the resistor values. And this information was covered in a previous video. So if you haven't watched that, go back and watch it. The parallel resistors have the same potential. They have different current. And we find the equivalent resistance by taking the inverse summation of all of the resistors. And then we have to remember that what we're getting as a result of that summation is the inverse value of the equivalent resistance. Okay. So now that we have that information available to us, let's take those ideas and we'll bring it back over here. And we need to ask ourselves, well, are any of these resistors currently connected in series or in parallel? And this is where I see a lot of students make mistakes with their concepts. To start, some of them might look at resistor 6 and resistor 3 and say, oh, well, they're side by side, they're in parallel, let's combine those in parallel, except they're not. If you remember, parallel resistors have to have their heads and their tails connected together, and we can't have anything else in between. Well, there is stuff in between. So I can't assume that resistor 3 and resistor 6 are in parallel, because they're not. Get rid of this stuff. I'm really starting to like OneNote. However, we do have a grouping of resistors here that are connected one after another. And that is the definition of series resistors. So I'm going to take resistor 2, resistor 3, and resistor 4, and I'm going to combine them into a single equivalent resistor and replace them in the circuit diagram. Now, anytime I do any kind of combination of anything in a circuit, I always redraw the picture. So resistors 1, 6, and 5, they're going to be exactly the way they were, but now at those two intersections, I'm going to replace resistor 2, 3, and 4 with one resistor that does the same job as what the three of them are doing. And technically this would be an equivalent resistor, but I'm not going to label this as equivalent because it's not the equivalent of the entire circuit. Instead, this is the equivalent of resistors 2, 3, and 4. And so I will just label that as resistor 2, 3, 4. And that is going to be included in my table. So resistor 2, 3, 4. What is the value of resistor 2, 3, 4? That's our next step. Well, resistors 2, 3, and 4 were added in series. So all I have to do is a direct summation of their values. Resistor 2 is 20, resistor 3 is 30, resistor 4 is 40, so that's going to give us 90 ohms. Now look back at my circuit here. I still really don't know anything about any of these resistors, so I am going to continue with my goal of combining resistors. But now we can see that resistor 234 has its head and tail connected to the head and tail of resistor 6. That means they're in parallel, and that means that I can combine them. So every time I make a combination, I redraw the circuit. So resistor 1 and resistor 5 remain as they are, but resistor 6 and resistor 234 are going to combine into a new resistor, and I will call that resistor 2346. I know this is not a very original naming process, but it does the job. Oops, 2346. And I need to know what the value of that resistor is. And to find that, since resistor 6 and resistor 234 are connected in parallel, I have to use the inverse summation method. And I will go ahead and actually write this information out. So resistor 2346 is the new equivalent resistor that I want, and I get that by taking the inverse summation of the other two resistors. So we have 1 over 60 plus 1 over 90. And I'll go ahead and put this together in my calculator. 1 over 60 plus 1 over 90 makes 0.027 repeating, so I'll round that off. But careful, that is not the value of the resistor that we want. That is the inverse. So to get the actual resistor value, we have to invert our answer, and when we do that, we get a value of 36. So 36 goes right in there. And we're one step away from our goal. I have a combination of resistors that are connected in series. And once I make a new resistor out of those, that new resistor, which we will now call the equivalent resistor, will be connected directly to our battery, and I will then be able to find out just how much current that battery provides us. We have 3 resistors in series. Series resistors add directly, so I need to take the value of resistor 1. I have to add that to the value of resistor 5, and add that to the value of resistor 2346. So what do we have there for our values? Resistor 1 is 10, resistor 5 is 50, resistor 2346 is 36, for a final equivalent resistance of 96 ohms. Alright, 96 ohms. I have a 96 ohm resistor hooked up to a 200 volt battery. Ohm's law says V equals IR, or I equals V over R. 200 over 96 gives us 2.083 repeating amps. Alright, well, so I know how much current is coming out of the battery. How does that help me? And if you've been wondering, when are we going to start filling in the other values on this chart? Well, now is the time. I just solved for the current that was coming out of the battery. That was the 2.08 amps. But where is that current ultimately going to have to go? It's going to have to go through that equivalent resistor. That's the only place it can go. So my equivalent resistor has to have a current of 2.083 amps. We also know that the equivalent resistor is connected directly to the battery, and so it has a voltage value of 200. With that, I now know everything that there is to know about this circuit diagram. So what do? Well, we backtrack. We're going to backtrack up to the previous diagram. And what we're going to do is now deconstruct the equivalent resistor. We're going to take our equivalent resistor and we're going to break it back up into resistor 1, resistor 2, 3, 4, 6, and resistor 5. But now I know how much current is coming out of the battery. It's the 2.08 amps. And that current only has one available path through the circuit. It has to go through all three of those resistors. And that is one of the defining characteristics of series resistors. They all have to have the same current. That current, 2.08, so that has to go through resistor 1, resistor 5, and resistor 2, 3, 4, 6. Keep in mind Ohm's law. We can now apply Ohm's law to those resistors to find out what the potential across each of those resistors needs to be. For resistor 1, oops, need to switch my color here. For resistor 1, we have 10 ohms. We have a current of 2.083, which will produce a voltage value of 20.83. For resistor 5, we have 50 ohms. We have current of 2.83. For a value of 104.2 volts. And then the last one is the potential for resistor 2346, and I think you see the pattern here. We're going to take the current times the resistance value of 36, and that's going to give us, I'm going to round this up to 75. Now it's at this point that I have all the information about resistor 1, resistor 5, and resistor 2, 3, 4, 6. My next step will be to progress up to the previous diagram, but I want to do a self-check of our work. self-check. So how can we check our work on the way so that we know that everything is correct? Because if we get something wrong here, we're just going to carry it back through every step along the way, and those errors are going to become more compound. Well, so here's our self-check. Remember what the potential across the battery is. It's 200 volts. And when I go from one terminal of the battery to the other, I have to account for 200 volts. Meaning, as I travel through the circuit, I can add up the potential values of each resistor, and if I get 200, then I know I'm on the right track. So here we go. The potential value of resistor 1 is 20.83. The potential value of resistor 5 is 104.2. And the potential difference of resistor 2, 3, 4, 6 is 75, which gives me a grand total of 200.03 volts. So I'm off by 3/100ths of a value, which I think would be acceptable as a rounding error. But I'm gonna keep as much information in my calculator as I can. Now I'm gonna erase this stuff so that I can make room for the next round of calculations that I have to make. Because now that we've done our self-check, we're ready to progress up to the next diagram. So here what we're doing is we're going to take resistor 2, 3, 4, 6 and break it up into resistor 2, 3, 4 and resistor 6. They are in parallel. Parallel resistors have the same potential, but what potential? Well, remember how we put all this stuff together. When we combined resistors 2, 3, 4 and resistor 6, they made resistor 2, 3, 4, 6. And those connection points have to be the same. Resistor 2, 3, 4, 6 had a potential difference of 75 volts. And so that same voltage now has to be applied to the individual resistors that made resistor 2, 3, 4, 6. In other words, resistor 6 and resistor 2, 3, 4. So this time around, we're not solving for potential, we're solving for current. I want to know how much current is running through each of these resistors. So in that case, I need the potential divided by the resistance. For resistor 6, we have 75 divided by 60, that's 1.25. And then we have 75 divided by 90, which is 0.833 repeating. So I know everything there is to know about resistor 6 and resistor 2, 3, 4. I already know everything about resistor 1 and resistor 5, so I don't even need to touch those. And we get ready to progress up, but before we do that, self-check. What do we check to make sure that we got the right answer? Previously, we added up the voltage values, but this time, you know, I can't add up the voltage values because 75 plus 75 does not equal 75. So the self-check here is that And let's see, I got to pick a different color here. I'm going to pick this purple. The thing that we need to check is the current that runs through resistor 2346. Well, that now has to be split up to run through resistor 6 and resistor 234. So whatever current that those two resistors have running through them is going to have to equal the current that ran through their equivalent. That's our self-check. So does the current running through resistor 234 plus the current running through resistor 6 equal the current that was running through their equivalent? So 1.25 plus 0.833, give or take a little bit of rounding error, that looks correct. So there's our self-check. We're satisfied that we're still on the right track. So we progress up again, and this brings us back to the original diagram of the circuit. And this step requires us to take resistor 234 and break it up into resistors 2, 3, and 4. Resistors 2, 3, and 4 are in series. Series resistors have the same current. But what current? Well, they are going to have the same current that was running through their equivalent. So all three of these get a current value of 0.833. And so now you can see just how fast this table kind of fills itself up. And we're going to use Ohm's law once again to fill in the missing pieces. We need the potential values of resistors 2, 3, and 4. We're going to take the currents times the potentials. For resistor 2, I'm getting 16.67. For resistor 3, I'm getting 25. And keep in mind what our self-check is going to be. Our self-check is that whatever the potential difference is across all three of these resistors has to equal the potential difference across resistor 2, 3, 4. Well, resistor 2, 3, 4 had a potential difference of 75, and we've already used up, let's see, about 42 of those volts. And so that leaves us left with about 33.3 volts for the value of resistor 4. Well, do the numbers match up? Is that what we get when we take the value of current from resistor 4 times the resistance value of resistor 4? And yes, it does. So now our table is completely full. We know absolutely everything that we could possibly want to know about every resistor in the original diagram. I know the current going through each resistor. I know the potential difference across each resistor. And like I said, now if we wanted to, I could ask questions like, well, what's the power associated with each resistor? And you have your choice of equations that you can use. There were 3 of those power equations. And you can use any one of those 3 on any of the resistors that you want because you have all the information available to you. Now, I'm not gonna ask for the power value of all those resistors. That's something that you can do on your own time. But what I will ask is how much, or let me start over. What is the total rate of energy dissipation for the circuit? So remember, every one of these resistors is producing some heat, and the rate of energy dissipation, that's just fancy terminology for power. And I want to know the total. What's the total rate of energy dissipation for the circuit? Well, I just said I'm not going to ask you to do all the individual resistors. So how are you supposed to get the total without figuring out the power values for all the resistors? Very, very simple. We're going to go back down to this this diagram right here. Remember, the whole purpose of having the equivalent resistor was that it would do the same job as the rest of the circuit. Not only does that resistor have to draw the same amount of current out of the battery as what the full combination of resistors do, but now that equivalent resistor is going to have to dissipate the same amount of power as what all those other resistors did in combination. But this becomes super simple now. It looks like probably our best approach would be to use the value of the battery and the value of the resistor. So that was this power equation. We have 200 volts squared divided by the resistance 96. We get our calculator out. And I'm getting 417 watts. So that is the total rate of energy dissipation for the circuit. And you can confirm that by finding the power values of all the individual resistors in the circuit. But I will warn you that if you're going to do that, keep in mind what are the actual resistors that exist in the circuit. It's just those 6. Everything else down here, this was just busy work to get us back to those individual values. Now, one last thing that I want to comment on before I end the video. We had all of these self-checks. Whoops, didn't want to do that. But, well, that's okay. I'll just redraw this. So we had all of these self-checks along the way where we would keep track of the potentials and the currents, and that all worked out really well because this whole table here that we made is kind of like a ultimate edition of Sudoku. Everything just kind of fits together perfectly, and if it doesn't, you know, we probably shouldn't continue. We need to go back and figure out what was wrong. But now we have an opportunity to revisit the idea of potential difference. The potential across across the battery was 200 volts. And we said it shouldn't matter how you get from one side of the battery to the other. You have to account for 200 volts. So pick a path. Any path you want. Maybe we start at the battery. We go through resistor 1, resistor 2, resistor 3, resistor 4, and resistor 5. Along that path, you must account for a total of 200 volts. So we go check all the voltage values. What do we have? Let's see, let's try red for this. We have resistor 1. Oops. Why is that moving things around? That's not what I want. That didn't work out well. Okay, I'll just circle them then. So resistor 1 was 20.83 plus 16.67 plus 25 plus 33.3 plus 104.2. And I'm guessing if you added all of those up, you would get 200 volts, give or take a couple of decimal values. So try another path. Try resistor 1, resistor 6, and resistor 5. Well, resistor 1 was 20.83, resistor 5 was 104, resistor 6 was 75. Add all those up, what do you get? 200. So these circuit combination problems are loaded with opportunities to check your work along the way. Now, I'm going to zoom out here, and I know this looks like an incredible mess, but it is imperative that you keep your work clean and organized when you're doing these circuit problems. I've actually had students that take this class coming from Circuits 1, and they're like, wow, this method here is so clean and precise and helpful. I wish I had known this back when I was taking circuits. So please use the table method. I promise you that it's worth the effort. Also, as you're combining resistors, make sure that you progress through your drawings so that you can see what's happening, and then you can very easily backtrack through your work, and you'll have a much better experience working with these kinds of problems. All right. So we're actually going to have a couple more videos on this chapter 27 material, and then we'll need to take an exam. So that exam will cover materials from chapters 25 to 27. The final topics from chapter 27 that we need to discuss are EMFs, multi-loop circuits, and RC circuits. And I'm gonna make videos for these two, and then Dr. Corey is going to take over with RC circuits. And so all of this I expect to have done by Monday of next week. These videos should be published, and then possibly by the following weekend we can expect a test. But I will contact you all with the specifics and the details once I know for sure what we're going to do. Alright, until then, see you at the next video.